Up to now, almost every force you study in physics has something in common. It's a contact force. If I want to lift this trailer, I have to touch it directly and put a force on it. And you know it's putting a force on me too. So the two objects involved, me the one pushing the trailer up, and the trailer the one pushing me down, are directly connected. This has been true of nearly every force you've studied so far. Springs are directly connected to the things they push or pull. The normal force acts on two surfaces that are being pressed into each other. Tension acts along a rope or a string or something that's hooked up to an object. The drag force, we forget there's air there, but that air is in direct contact with objects moving through it. And friction is two surfaces moving past each other. But there's one force you've studied, gravity, where the two objects involved in the force are not connected at all. We say this force acts at a distance. This difference bothered people studying gravity from the very beginning. In physics, we look for patterns. As I change variables, what happens to another? If we talk about a mass on a spring, if I start varying the mass, the spring is going to have different effects on motion. But it's obvious how the mass and the spring can affect each other. They're touching each other directly. The information of how big the mass is immediately available to the spring. But if you're talking about something flying through a room, how does the Earth know about that object? How can the Earth affect that object's motion? But we see that it does, and it does it in a really clear pattern, one that you've now studied quite a bit. So there must be something going on, some way of information being exchanged between the Earth and the object that was flying through the air. Gravity is not the only force that acts at a distance. We'll see that it happens with static electricity. So now, as you can see, the styrofoam spheres, they all have a charge, and they're all pushing off each other. And they're repelled by the rod because they all have the same type of electricity, the negative electricity. And that's creating a force, and it's a force we can study just like every other force in this class. And it's kind of fun to do this for a while. And even these magnets can act at a distance. We basically use a concept called a field to help us describe forces that act at a distance better. And a field is something you can visualize as altered space. So if I have one object, and we'll see it could be a mass, it could be a charge, it could be a magnetic pole, that changes the space around it. And that altered space therefore interacts with other masses or charges or poles and causes forces on them. In its easiest to understand form, you could think of the gravitational field as being like a map of what forces we would have if we put an object in a certain location. Typically, if we're talking about a room, the gravitational field is pointing down because anywhere we put an object in, say, a classroom, it's going to experience a downward force. But when we zoom out and look at the entire Earth, we see that if we move the object to different locations around the Earth, the direction of the force on it would be different. And therefore we have an inward gravitational field. And really this downward gravitational field is just a small piece of that. It turns out that both of the equations you've studied for gravity can describe these fields. So let's take a look at how that happens. So I've drawn this planet here. It's supposed to be Earth. And I've drawn several masses around it. Notice that they're all at the same height above the Earth. Well, if we were going to go calculate how much gravitational force is on each of these, we would have to use Newton's law of gravity. And I've done the calculations for each color of the masses here. And you can't help but notice when you do it all in the same color that most of the equation is actually identical. Big G is the same in all of them. The mass of the planet is the same in all of them. The only thing that's really changing is the mass of each individual object. So if you run with that idea that the force of gravity is really two parts, something to do with an individual object, its mass, and then something to do with where it is, it gives us new respect for the original gravity equation we learned at the beginning of first year physics. Force of gravity equals mass times acceleration of gravity. Force of gravity equals something to do with the object times something to do with where the object is. So little g is actually a quantitative measure of how strong gravity is in a location, and we call it the gravitational field. We can solve for little g by setting the two equations equal. If we do that, one of the masses cancels, the mass that had to do with the specific object. The other mass doesn't, the mass that has to do with the thing causing the large gravitational field. And we're left with an equation. And it's important to see in this equation, big G is a constant, this mass has to do with where you are, and this distance has to do with where you are. This is all about your location. We could draw something known as gravitational field lines that would help us keep track of the force of gravity at each location. I'm going to draw lines going into the Earth, evenly spaced around the Earth. And what this represents is how strong the force of gravity is at various distances from the Earth. We know it's stronger when you're close. We know it's weaker when you're farther away. And if you look at these lines, which are in the direction the force of gravity would be at every location, you can see that they're spreading out, just like gravity spreads out. So where the lines are closer together, you have a stronger force. Where they're more spread out, you have a weaker force. And that means the field is strongest when they're closest together. So we could go through and calculate what the field is at every distance from Earth. But the picture gives us a general idea of what's happening and represents how strong the field is. So it's even more important that we do this with the electric force. Let's say on my Van de Graaff generator, I put a positive charge all over my dome. Well, I've got a +2 here, a plus, a -3, a -2. These charges are all going to experience very different outcomes. Some are going to be attracted, some are going to be repelled. The strength of attraction and repulsion is going to be different. But the environment they're in is all the same. So it's important we keep track of the environmental effect versus the effect of individual charge. So the electrostatic force is something we're going to look at in great detail in this course. And for a pair of point charges, you've probably seen the equation. It's known as Coulomb's law. And it looks like it's got almost the same form as Newton's law of gravity. I've got the two of them next to each other here. There are some key differences. Obviously, we can have a positive or negative charge, and if we bring other charges near those charges, there's going to be opposite effects. So you can see that I've got the same little charges around my two big charges, and they're experiencing forces in opposite directions. Also, negatives are going to be attracted to negative charges, positives are going to be repelled. So the electric field is slightly more complicated. What we typically do is we draw field lines going out of a positive and into a negative. And we just remember that there will be a force on charges. And if there's a positive charge brought into our field, it will experience a force in the direction we drew the lines. If there's a negative, it will experience a force in the opposite direction. Notice that we can have a situation kind of like the constant gravitational field in our room in between a pair of parallel plates. This is something called a capacitor, and we'll study this quite a bit in our class. A positive charge would kind of fall towards the negative, just like a ball would fall down in the room. A negative would float towards the ceiling or float towards the positive. Notice also that we end up with an identical set of equations. If you've understood Fg equals mg, you should understand Fe equals Qe. We just replaced the gravitational field with the electric field, and we replaced mass with charge. And here's the equation for the electric field near a point charge. This is only valid if you've got a single place where the charge appears to originate from, a point charge. Just like this is only valid if you've got a single large mass, like we do near Earth. We typically in high school physics don't see situations where we're not near a single large mass, so this is almost always our gravitational field. We will definitely see situations in this class where we will have multiple charges, and that will cause fields to go in different strange directions. But again, positives will move with field lines, negatives will move against them. And we can always calculate the force on an object as long as we have a quantitative value for the field. You probably remember that back when the only thing you knew about the gravitational field was that it was 9.8, you could always find the weight of something by doing its mass times 9.8. As long as you know a quantitative value for the electric field, you could find the force on a charge by doing a charge times the electric field. So this equation works always, not just when we have point charges. What I'd like to do now is talk about a related concept to force, potential energy. And I want to take this idea that field is the location part of force, and then to find force you multiply the object's information by field. It turns out we could do something like that with potential energy as well. If you think about potential energy, it's defined as the work done by a conservative force, sort of. Let's imagine me lifting a textbook. I lift it from a lower height to a higher height. I'm moving it up. Well, I'm doing positive work. That's the energy that is eventually going to be in the book. But the conservative force here, gravity, is doing negative work. It's stealing the work I'm doing, but it's not making it go away. It's conserving it because it's moved in the field. And we actually defined potential energy by using the work equation, FD. The work done by gravity is negative FGD. And we've just really talked about how the force of gravity is mass times the gravitational field. So the gravitational field affects the work you do. We define the potential energy as the positive of that, and that's where we get our simple equation mgh. So motion of a mass in a gravitational field affects your potential energy. So there's a concept that's kind of like gravitational field, the location-specific part of force, but it's actually the location-specific part of potential energy. We call that potential. Potential isn't the location-specific parts of force. It's the location-specific parts of energy. And I want to show you what I mean. I've drawn the same masses I had before, and I want to envision that we're grabbing one of these masses, we'll say this purple one, and we're pulling it out to a higher distance from Earth. In other words, we're giving it more potential energy. And I've done the same with the other three masses as well. So if we were going to look at how much potential energy any of these masses had in one of the two locations, we would take the equation for gravitational potential energy. Now this may not be something you learned in your specific class. Some classes will learn this, some will not. But just like with force, a lot of the equations depend on where you are, and only part of it is specific to the mass you've got. And the reason, of course, is that we started out with all of these objects at the same distance from the center of the Earth. So part of their potential energy was all the same. And the exact potential energy only varied based on their mass. The same is true when we got them farther away. They're all still the same distance from the Earth, but they moved to an area of higher energy. And how much higher energy? Well, part of that calculation is the same for all of them. Let's look at the simplified situation of just gravity in this room so we can see how part of the equation remains constant
regardless of mass.
So you know the equation for gravitational potential energy. It's PE equals mgh. And I'm going to define something called gravitational potential. We'll call it Vg for gravity voltage. And it's going to basically be potential energy divided by charge, or excuse me, by mass. We're doing gravity, not electricity. So what would that end up being? It would be mgh over m. And we get the obvious cancelization of mass. So we're just left with gravitational potential is GH. So I have a 50 kilogram mass and a 1 kilogram mass sitting here on the ground. And they have no potential energy because I've defined the 0 point for height to be the ground. But go up a meter, of course they have potential energy. I did work to get them there. They have different potential energies, but that's entirely because their masses are different. If you look at the other part of the calculation, the GH, the 9.8 times 1, that's the same. And this, obviously it's true if you go to 2 meters as well. So this is just like the relationship between gravitational force and gravitational field. We had part that depended on the object itself and part that depended on the location. Well, look at the potential energy calculation. Part depends on the object and the rest depends on location. So we call the part that depends on location the gravitational potential, GH. Gravitational potential energy, mgh. So another way of saying gravitational potential energy is the object's mass times the gravitational potential of that location. If you know the gravitational potential of that location, you can calculate gravitational potential energy. The same is true with electricity. If you have a constant electric field, like we had a constant gravitational field, and we do experience that between oppositely charged plates, electric potential is just E times D. In general, though, that equation where we multiply the object-specific property times the location, that's the most useful equation involving electric potential. If we want to know the electric potential energy of something, we multiply its charge times the potential in that location. Just like there's clearly a big relationship between gravitational field and gravitational potential, there's definitely one for electric field and electric potential. So here's a positive point charge, and I'm going to use my cursor as a little positive test charge. Obviously, the two positives repel each other, so if I put my test charge here, we would experience a force in that direction. But if I started to do work and push it inward, each of these rings represents a different location, and that ultimately is going to affect how much potential energy I give it. You could kind of think of it as pushing a ball uphill. In fact, we can visualize the electric potential in a field like this as kind of like being a hill. If I'm going to push this positive test charge inward, it's like I'm going to have to push it where it doesn't want to go, or uphill. And the more I push it, the more potential energy I get. And if I let go, I lose that as kinetic energy. The opposite, of course, is true. If I had a negative point charge, I would actually be experiencing a force inward in this case. And that means I'd be losing potential energy as I go closer. Each of these rings would represent less and less potential energy. It would almost be like a ball rolling downhill. So we can visualize the potentials in that situation as being like a well. My positive charge here actually has a lot of potential energy, and it would lose it and convert to kinetic as it rolled towards the negative test charge, or negative point charge. So I suspect what you're feeling right now is that all of this is interesting, but you don't know why we need this whole concept of potential. It doesn't seem like it's hard particularly to use just simply electric potential energy or gravitational potential energy. The reason for that is that we actually can put lots of charges in a location, and both the electric fields and the electric potentials can get complicated. So, for example, if I had two positive charges here, visualizing the potential, we get these two peaks, and the motion of my positive test charge, if it's brought in, could actually be complicated. It would roll down here, but it's not going to want to go this way because there's another charge. So it'd be like rolling off a saddle. And it looks pretty different if you have a positive and a negative near each other. We have complicated fields and potentials there. That would look something like this. So the ability to find out everything you can about a certain location and then be able to determine what kind of forces and what kind of potential energies a charge has is something really important. So I'm sure all of that looked complicated, but the equation for electric potential energy, we use a U typically so we don't have to write two letters like PE. The equation for electric potential energy is pretty simple. If you know the potential in a certain location, you just multiply by the charge, and you know how much energy that charge has. So this is a lab we'll do, and we can put various conductors on this piece of conductive paper and hook them up to a power supply. And no matter how complicated we make those conductors, what shapes we draw, we can easily figure out the potential in every location on the paper just by using a simple meter, this voltmeter. So every one of these locations has a different potential, and if we were to put a charge in those locations, we could easily find out how much energy that charge has. Remember, potential totally just depends on location. Often surprising to students that I'm willing to shock myself with a Van de Graaff generator when I tell them that the potential on the dome is 300,000 volts. Volts are the unit for electric potential. Let's take a look at that. It's also perfectly capable of taking electrons from me. Ow. I don't know if you could see that bolt in my hand. The reason that was relatively safe to do is that potential energy, the thing that would actually do work on me and mess me up, is Q times V. So although I have a huge potential difference between the floor and the Van de Graaff, which is why I got shocked, so little charge transferred that it still ended up being a small potential energy. So we had a few charges falling a huge distance on those potential hills you saw. It wasn't enough to hurt me. Electric current coming out of the wall or even a car battery, it's not really safe to try to shock yourself like that, because although it's a much smaller potential difference, it's a much larger amount of charge, so you can have much more energy delivered. So it's important to understand that we have to care about the distance each charge falls, the amount of energy each charge carries, if you will, but also the number of charges we're dealing with. Worth mentioning that the last type of field we'll study this year, the magnetic field, it also tells you how the space around a magnet is altered by the magnet's presence. There's a few differences, though. The first is that although we can have a single electric point charge or a single mass, magnets come in what are known as dipoles. We always have to have two poles, a north pole and a south pole. One place where the magnetic field leaves and another where it enters. So that's a little bit different. You can use the field to tell you the direction of the force, but it's not as simple. Unlike with electric and gravitational, where the force is in the same direction as the field or directly opposite, if this was a negative charge, we're going to see that it's in a very different direction with the magnetic field. So this idea of altered space around something we're studying, it'll be important for magnets too, but it'll be more complicated. So that's a lot, and I don't want you thinking you should understand it all now. We'll be spending a lot of time on this. The big ideas are the same big ideas that you had in your previous physics classes. sigma F equals ma, and energy original equals energy final. All we're doing is applying this now to forces that act at distances. You put a positive charge in space, it's going to cause an electric field. That electric field is going to cause forces on any charges you bring nearby. And you can use the field to help calculate those forces. You put a positive charge in space, that's going to cause any charges anywhere else in space to have certain potential energies. And you can use the potential at each location to calculate the potential energy different charges would have. So these are useful concepts to help us understand action at a distance and apply the same big ideas from our previous classes to charges and masses with these strange forces that act at distances.